Exercise 130, question 5. This is a required question for the BTEC course, so I'm not going to do that particular question, but I'm going to do one that's very similar, and then you can have a go at the one in the textbook and see if you get the answer. The problem here is that I've got three components connected in parallel. 1, 2, 3. So I'm going to call them Z1, Z2, and Z3, all connected in parallel. So remembering how to add up resistors in parallel or impedance in parallel, 1 over ZT, the total impedance, equals 1 over Z1 plus 1 over Z2 plus 1 over Z3. So we've got to work out what the total impedance is using this formula. We're after the current. So as we've done before in these sorts of questions, we're after the total current in the circuit and its phase relative to the voltage. So I equals E over Z as before, where Z is the total impedance. But actually, if you think about this formula for a second, this is exactly the same as E times 1 over ZT. So all I've got to do is work out what 1 over ZT is and multiply that by the voltage to get the current. And that's handy to realise because 1 over ZT is in fact what this formula here gives you, 1 over ZT. So I need to work out what 1 over ZT is and then multiply that by the voltage to get the current. My current needs to be in polar form, so I'm going to end up with my 1 over ZT in polar form and then do a polar multiplication. So see if you can continue and complete the question. So first step, find out what 1 over ZT is. So it's going to be called 1 over Z1, which is 20 minus 10J, because it's a capacitive reactance, plus 1 over Z2, which is 40 plus 20J, plus 1 over 10 for the last leg. So I need polar form for this, and I've got a division. This is a division to do, so I need to divide 1 by that, 20 minus 10J. So convert this to polar, and then remember that 1 is a real number, so that's 1 angle 0, and we can do the division. So do that for each of these legs. The last one's just a real number, and then you can add them all together to get the 1 over ZT. So 1 over ZT equals So it equals 1 over 22.4 angle 26.6 plus 1 over 44.7 angle 26.6 plus 0.1. So now I need to do the polar division. So each of these is angle 0. So divide the moduli, 1 divided by 22.4, and then subtract the angles, and so on. You get the answer. So there, in polar form. Now I want to add these. Can't add in polar form, so I need to convert each of these to rectangular form to be able to add them. So 1 over ZT equals 0.04 plus 0.02J plus that 0.02 minus 9.9J plus 0.1. Notice that I'm rounding all the time here, so we've got an error creeping in all the way through. So trying to hold accuracy, you can try and hold more significant figures throughout. So now finally we can add these real and imaginary parts together to get 1 over ZT. So now we have 1 over ZT. We now need to plug this into Ohm's law, if you remember, to get the current. So I equals the voltage, which is 120 volts, times by 0.16 minus 9.88J. So now I equals So we multiply out the brackets, 120 times 0.16, 19.2, and then 120 times minus 9.88, minus 1185.6. So finally we need to convert this to polar form so we can get the value, the magnitude of the current and the phase relative to the voltage, which gives us a very high current and almost completely 90 degrees out of phase with the voltage. So in practice this wouldn't be a very good circuit to set up. If you think back to basic electricity, when you add resistors in parallel, you effectively end up with reducing the resistance, the overall resistance. So we've got 120 volts over probably quite a small impedance, so you're going to get a large current. But the principle is correct for the question number 4, so have a go at that now, or question number 5 rather, have a go at it.